So today I just wanted to go through very briefly over the past, the research we've done over the past 3 years and sort of elaborate on some of the findings that we've done in research and how that made directly into practice. And I have 45 slides, and Cam told me that I have 15 minutes, so I decided my solution will be I just go faster and I'll click the button a lot faster. And so we'll see how that goes. So my professional career has taken a completely different turn after the Canterbury earthquakes, and that was one of the first flights after the airport has reopened. I was there in Christchurch and lived for about a year. Along with Lisa Moon, we spent that time inspecting pretty much every single building, unreinforced masonry building in the Canterbury region, and I think in total we've inspected about 650 buildings. And that has proven quite useful because the data ended up being used in Royal Commission's publications, and we're still crunching for all that information, and it's been really good. So because I'll be flicking through the slides very quickly and mentioning things exceptionally fast, you'll see at the bottom of each slide there's a paper or a report name that will refer you to more information. And a lot of the stuff has already been presented at different conferences and papers, so this is essentially a summary all put together into one presentation. So we started the journey with little scale things. We looked at extraction of mortar samples in order to establish material properties for masonry buildings. So along with some peers in the university, we established a technique where we extract little baby samples from masonry buildings, and we compress them and extrapolate to sort of the global material properties of the building. We then modified various techniques from overseas in order to establish shear strength of buildings. We also used sort of more fancy techniques where we resorted to using ground penetrating radars to establishing voids within masonry buildings and interconnection, particularly for the stone masonry buildings. So we then moved to doing more looking at assemblages, and then we established different coefficient factors, cohesion for masonry with different mortar mixes and different aggregates for mortar mix. And all of this good stuff ended up in the NZSE section C8. And so what's been done later is, again, one of the pioneering studies with material stuff is we looked at the transitioning point between where the failure mode actually happens within the mortar joints, as you can see in the picture on the left there, or a brittle failure that happens directly through the brick. And we've done a number of relatively large walls that we used quite a different variety of mortar mixes, different brick strength, and quite neatly established a transition point between the failure modes. And that quite nicely ended up being in the newly released section C8 as well. Using the data collected from the Canterbury earthquakes, we looked at all the parapets we could possibly find. There was just under 1,000 of them, and we surveyed those and established cross sections and heights and etc., failure modes, and that helped us to guide us to conceive an experimental program where we conducted shake table testing of as-built parapets. And essentially the key takeaway point from that was that you could resort to using displacement-based assessment techniques, but at the same time, a simple static analysis of the parapet gives you quite accurate results, which was quite a neat finding. We then decided to do something even cooler. I think this is actually the world's first test of a full-scale vintage diaphragm. We found a building in Wanganui where we developed this unique test setup and sliced and diced a diaphragm that was 100 years old, and we pulled it in order to establish strength and stiffness, and that quite fortunately ended up being fed directly into the NZSE guidelines. So that was my favorite, actually. The other vulnerable aspect of masonry is a cavity wall construction, and one of the first things we've seen in Christchurch is collapse of cavity walls. So we've again resorted back to the database collected from Canterbury and established different failure modes in geometrical configurations, and based on that developed and conceived an experimental program. And one of the key takeaway points from here is that basically the cavity walls respond as single leaf walls and quite vulnerable to failure, and I think we all kind of knew that. This is some of the work that has been done by Charlotte Thoma. This looked at the in-plane failure modes of spandrels, but I'll skip to that really quickly. Then we looked at more of a global performance of buildings. So up to now we looked at just assemblages and components, and I really wanted to look at the global performance. And so this particular study will be presented 3 presentations after me, so I don't want to steal the thunder from the presenters. So then we thought, well, how about we make it even more extreme? We tested a full-scale building that was up for demolition over in Auckland, just around the corner here. And what we've done is we put little shake tables on the building, and we excited it and determined the dynamic properties of the structure. We then removed the partition walls extremely quickly from different walls, from different layers, different floors of the building, retested the building and seen how the dynamic characteristics has been changed. But then that was not crazy enough, so we got into a bigger excavator and we pushed the building across. We recorded the forces and the displacements, which we then used to compare to the results that we would get using NZAC assessment guidelines and AAC as well as different modeling techniques, and that aligned quite nicely. So that brings me to more around the topics of retrofits, and we've seen quite a number of case studies in Christchurch where retrofitted buildings, unreinforced masonry buildings that were retrofitted before the earthquakes performed extremely well, and so we wanted to dig deeper into that because that was quite a unique data set that not many other countries around the world have access to. So the first thing we looked at is some of the buildings. I think there was 7 case studies in total, which had steel frame retrofits. Some of them were what we considered as flexible steel frame retrofits, and we've been looking into why some of these buildings perform extremely well, and just digging deeper, doing sort of a forensic study around this, and this is still underway. We reported performance of this particular building. This is actually still in existence in Christchurch in the Arts Centre. It's been reopened to the public, I think, just recently. And it used vertical and horizontal post tensioning, as you can see, externally positioned throughout the building, really cost effective, and from what we've seen, performed extremely well. So we were really interested in looking at this case study. There was a number of FRP building retrofits as well, which I will want to mention here. Some things that haven't performed extremely well is the epoxy anchorages, and I think we've alluded to this, and Jason mentioned in his seminars about this issue. And I think just as a general statement, we found poor performance of adhesive anchors in about 50% of the cases that we inspected. So it's quite a frightening statistics, and a lot of those, from our observations, were due to poor construction and poor quality control on site, perhaps. And also looked at the plate anchors as well. So that got us thinking about doing a whole experimental program around epoxy adhesive installed anchors. And so we went and we found buildings around Christchurch, Auckland, and Wanganui as well. And we have tested something like 650 anchors with different configuration, different epoxies, and all that good stuff has actually been ended up in this section C8 as well. And similar exercise has been repeated with the plate anchors, where we've tested existing plate anchors that were almost 100 years old, and then we tested new plate anchors as well, and some of that stuff again ended up in the NZAC guidelines. This is probably another world's first where so anchors don't always act just in pure tension. When we load anchors in shear, we need to know what the capacities are. And so an experimental program where we've done quite a few dozens of different configuration of anchors, tested them in various cycles, and once again that was fed directly into the NZAC guidelines for the assessment. One of the first things that anyone sees when they are in a following earthquake is a collapse of chimneys, and that's all good, but we also looked at some of the chimneys that were retrofitted or braced, and those haven't really performed adequately as potentially expected by the designer. So we started a little experimental program where we looked at the performance of the as-built chimney, and that's the one that you see shaking around there, with very weak lime-based mortars. We then looked at creating retrofit techniques. So one of the first ones we tried was using FRP strips positioned within the masonry, vertically extending down just below the flashing level, and that performed quite considerably better. What we did later is we positioned the vertical threaded rod right in the middle of the chimney and essentially just clamped it top and bottom and tested with different exo loads, and even with an exo load that had just hand tightened, we still managed to quite considerably improve the performance. So that got us thinking that we need to do it in a full-scale house. So we were fortunate enough to have a building owner, thanks to Patrick Komolsky from Malton Council in Mission Bay, with I think a $3 million house, who donated us his chimney for testing. It was very generous of him. And so we tested the chimney, as you can see, using a very innovative pulling system. And we tested it in the as-built condition, and then what I've done is, through the scaffolding, we have lowered down a threaded rod all the way down to the bottom of the chimney, clamped the whole thing together, retested it, and essentially the takeaway point from all this experiment was that we had a very earthquake-prone chimney, and by sort of doing a retrofit that took us less than an hour, we took it up to 67% ABS or above. Looked at different restraints, parapet restraints, especially the performance following the Canterbury earthquakes, and that got us into developing and conceiving an experimental program where we tested different bracing systems. I'll run these both simultaneously just because we're running out of time. And the whole point here is you can see the accelerations are actually quite large, and what the subsequent steps of this study is we want to develop a number of standardized solutions that engineers could potentially use. We'll be flicking through this very quickly, but we looked at diaphragm strengthening. One of the techniques is using very thin plywood overlays, or simply renailing the diaphragm, which has their own benefits and disadvantages. We then looked at the installation of perimeter cords, but of course diaphragms are acting as shear beams and not flexural beams, so perimeter cords did not really influence the performance as much as we wanted to. We looked at using fire-rated ceilings as well, because as part of the upgrades, some of these older buildings require fire systems to be upgraded, so the use of fire-rated ceilings, and we subjected the diaphragm to lateral loads. And that didn't work as good as one might hope, because after certain periods, certain amounts of drifts, we had the sheets delaminating and actually coming down from the ceiling. We looked at a number of retrofit techniques for strengthening walls in plan and out of plan. So this is an example here using near surface mounted little baby carbon strips embedded into masonry, and more recently we've also used steel wire rope that's been positioned in the same manner. And I think we've got at least a dozen of buildings around New Zealand where this technique has now been implemented. Some of you might have seen this on the CSOC presentation and the CSOC journal. We developed a technique where a simple timber framing, vertically positioned, sort of 90 by 45 timber studs from Bunnings, and connected top and bottom with specially designed screws, regularly positioned, and that has extremely well improved the capacity of the walls in the out of plane direction. We then developed, I've got 2 minutes to go through another slide. We also developed the similar technique for cavity walls. We then put all this on the shake table in full scale and make sure that we validated and the technique actually worked. So up to this slide, everything that we've done, something that you can possibly even use after lunch and start implementing that in your project, so quite practically orientated. The next couple of slides, I think I've got about a minute and a half, I want to quickly skim through some of the more future research that will, in the future, potentially end up in some sort of practice. So we've done using discrete element modeling, which models individual bricks and mortar, and we calibrated this particular models in the out of plane using simple pushover tests, and relating that back to some of the airbag testing that we've done in the university. We then further calibrated the discrete element models using two-way bending experimental results, and you can see how that was quite nicely correlated. We took it a step further and used the shape table data in order to further validate these discrete element models. And then we used the global building that we'll see in a couple of presentations that we used as well to calibrate this model. But all this is good, but it takes quite a few hours to run because our computing is not yet ready for such modeling in a practice perspective. So that we used something that's been quite popular and been hitting the news lines very recently, or is the use of drones. And the use of drones are actually quite cool because we can collect huge amounts of information really quickly and really cheaply. And so this is a model of Oamaru, it's a three-dimensional mesh of the building structures, which was collected in a matter of minutes. We've done that for Oamaru and other parts of New Zealand as well. Yep. You can use photogrammetry in order to build interior models of buildings as well, and I think some of you might have seen this before. Just 1 minute. Hopefully you're finding this interesting so that I'm not just stealing your time. We then used the LiDAR scanners, scanning data, which is actually publicly available in this example here from Otago Council. We used this data and then calibrated our photogrammetry models and found that we are getting a difference of maximum about 100 millimeter difference. So I think this is quite good considering that we take very little time to accumulate that large number of information for building communities. And the ultimate goal is to try and model in real life the performance of building communities. So of course using the discrete element models that I've shown you before is not feasible because of the computing time. So we resorted to something that is more of a what's called Blender, used for special graphics and gaming, but it has physics embedded into the coding. And you can see here it still needs some work, but this considerably decreases the running time, and we can do quite a lot of cool things really quickly. Last thing, I'll skip through this. This is another very cool thing you can do with Blender. Artificial intelligence is the next thing on our radar, and very quickly on this slide, this is what an autonomous vehicle sees when it drives along. And you see Tesla driving around Auckland, this is what it actually sees. And just keep an eye on how awesome this algorithm is. This is in real life. It picks up the pedestrians, picks up the road signs, the color of traffic lights, etc. So it does take considerable effort to train an algorithm like this, but once you do it, it's quite amazing what you can do. So what we've looked at is utilizing this for earthquake engineering and doing that for damage identification. And in conjunction with University Cal Poly in California, we've been looking at the study of training algorithms for damage. So it's like Facebook for buildings, if you like. It identifies certain damage depending on how you train it. So you can see how I transitioned from crashing mortars to all the way down to using artificial intelligence. And I just want to leave you with, before Cam really kicks me out of the stage, leave you with this phrase here. I borrowed it from John F. Kennedy, but we would like to have input from the community and from the industry and help us drive the future of research. So thank you very much.